So what we're going to be looking at in 8.2 is we're still going to be looking at trig functions on a coordinate plane, talking about domain and range, which you saw in 8.1 once we looked at sine and cosine. But now we're going to look at all the other 4 trig functions. So 8.2, we're going to be looking at graphs of other trig functions. Graphs of other trig functions. And so the first one we're going to start with is tangent. In 8.1 we did sine and cosine, so it kind of makes sense that we look at tangent next. And I want to look at not only some basics of it, the period, the amplitude, possible asymptotes that it can occur, but we're going to look at table of values, and we're going to relate it all back. Now, in 8.1, we looked at sine and cosine, and we talked about how there are functions that after a certain period, they start repeating, and we could see how that occurred. So I want you to remember here that when you're looking at tangent x, this is the equivalent of sine over cosine. So some of the things are going to be related as we go. You can see in earlier sections and chapters that when we start talking about trig functions, if we can figure out what's going on with sine and cosine, everything else falls out, because tangent is equal to sine over cosine. Sine, cotangent, secant, cosecant are all related back to these first 3. And so that's why you're going to kind of see these progressions as we go. Now, one thing to note is we have talked about how even and odd functions. So this is an odd function. Sine and cosine, one was even and one was odd. So if I divide them both out, I'm going to get an odd function and some characteristics from there. And the first thing I want to do is I want to start with the table of values, okay? And we did this in 8.1 as well. So if I do my table of values and I look at my x values and my y values being tangent of x, I'm going to look a little bit different at these. You'll notice with sine and cosine, we kind of stayed in quadrant 1 with our values. We only look at positive x values as we do our table. But with tangent, I'm going to do some other ones. So the first one to look at, I'm going to say negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, 0. Go the other direction, pi over 6, pi over 4, pi over 3, and then positive pi over 2. Now again, as we're looking at these table of values, remember that and this is a 3 right here. Remember that your trig circle is very beneficial. So for us, when we're looking at the trig circle, we can use our cosine and sine values and the fact that sine over cosine is equal to tangent to figure out these positive angles. Now, when I drop into the negative angles, remember when you're working with your trig circle, when I go up like this would be the positive of the angle, but if I drop down, this would be your negative angle. Okay, so your trig circle is still beneficial to you, but instead of looping around, we're going to be dropping down from the x-axis to get those negative ones. And so each time that we do this, we are going to be looking at the sine over the cosine in order to get our table of values here. Now, the first thing that we're going to notice is that when we do negative pi over 2, so think about this, negative pi over 2 is right here. When I start doing sine and cosine, I get division by 0. Because remember that ordered pair down here? And so it is actually undefined. And we'll look at why and how that affects us here in a minute. Negative pi over 3 is going to output negative square root of 3. Then we get negative 1. Negative square root of 3 over 3. 0. Square root of 3 over 3. 1. Square root of 3. And again, undefined here for the same comment of how we were up here on pi over 2. Okay, and now remember with this, your calculator does do radians and it does do sine, cosine, tangent, etc. So you could have inputted a couple of these in your calculator using your radians, make sure it's in radians, but it's kind of hard to get an output of square root of 3. So your unit circle is also great with that. Now when I start kind of graphing these together, I want you to think about this. Let's kind of draw a graph. Now we are going to move into transformations of functions like we did with sine and cosine, but I just want to start out first with just our basic tangent of x. Now, let's think about this. We can see that our x values are going to be in radians, and so I'm going to mark those accordingly here. And then I can see that my y values are going to be in kind of some numeric values without pi in them. So I'm going to kind of make my graph accordingly here. I am going to just go out 2 marks here, talk about negative pi over 2, pi over 2, and pi. And then, let's see, let's just kind of count it up from here. And what this graph kind of looks like is, you can see that at negative pi over 2 and pi over 2 that it's undefined, and that's because there is a vertical asymptote here. So I'm just kind of take a different color here so you can see that this is not my function, nor is it an axis. It's just kind of an imaginary line that we're not going to be able to touch. I see that at 0, 0, I have a point. And then as I move through these, I can see it maybe, you know, pi over 4, I'm at 1. And negative pi over 4, I'm at negative 1. Something like this. And so what this graph creates is something like this. And so it kind of resembles, I'm sorry, you couldn't see all that. It kind of resembles what's kind of going on with almost a cubic function. And what happens is this repeats every period. And so if I were to move over here and maybe extend this out to 3 pi over 2, I would see the same thing kind of occurring. And so just like sine and cosine, it does have a period to it, which we're going to identify that here in a minute. And then it kind of cycles back through. And again, this would also occur over here. I guess I should have made this graph a little bit larger. Okay, so you can kind of see 3 of the graphs there that is happening as you're working with your tangent. And so some things to notice, if you were to pick some values as you got really close to this pi over 2, and then also really close to pi over 2 down here, you could see how they would go up very largely and come down very small and go down into those quadrants. As we move through our tangent, this is just our basic graph, so our functions should resemble something like this, but I want to work with some and talk about how does other numeric values as they are put in there affect them? How can our transformations kind of occur with them? And we looked at this with sine and cosine, so let's just kind of do some features here. And so let's just call this part A, and let's move down here and talk about part B. Now, as I kind of break these apart and look at these other 4 trig functions, I'm going to break them into two kind of notions here. Let me kind of adjust our camera here. The first one I want to kind of look at is graphing y equal to a tangent of bx. You'll notice when we're looking at sine and cosine, we really had a very general form of, had a lot more going on with it. As we look at these next 4, I'm going to break them apart. I'm going to look at y equals a tangent bx, and then we'll add in some more transformations and kind of look at some stuff that comes from it. So first of all, to kind of notice with this one, we can notice that there's going to be a stretching factor. Is the absolute value of a. To kind of talk about how it may be stretched, it's going to be looking at your a value. When you look at the period of this function, we can already kind of see that the period here, notice it went to pi over 2 and a negative pi over 2. And so its period in the basic function was pi, right? If I do the distance from this to this one, it would be pi. And so if I'm looking at the period p, it would be equal to pi over the absolute value of b. So I'm going to take my normal period of pi that we saw in the tangent x function, and it's going to be divided by the absolute value of b that I get from here to figure out my new period. And so that's going to help us to maybe start by setting up our asymptotes. Some things to remember in regards to the graph. The domain of this is all real numbers, and you can just write like an R with a double stem on it here, all real numbers. Or if you forget what that is, just put your little parentheses and write all real numbers. And we also say it's all real numbers where x does not equal pi over 2 absolute value of b plus absolute value of, let me start on here. X does not equal pi over 2 absolute value of b plus absolute value of bk, such that k is an integer. So this is just a very general way of talking about where the asymptotes occur. And so your domain is going to be all real numbers except for at those asymptotes. And so we'll kind of look at this here in a minute and how we can set up that domain, but that kind of gives us a formula. Now, if we start to talk about the range, your range is your up and down. Notice up and down, I don't have any problems there. You can see that my values are going to go up to positive infinity and down to negative infinity, and that's just looking at this small area here. So my up and down is not a problem. That side to side, I'm having to compensate for all of these asymptotes that it's creating. And so the range for this is going to be from negative infinity to infinity. We can note that the asymptotes occur at these values that we've already written out and that we restrict it from our domain. So I'm kind of writing that in another color there. And so kind of putting this all together, I want to kind of look at an equation, identify some stuff, and graph it, okay? So there is just some guidelines or characteristics for graphing a y equals a tangent of bx. And so let's do an example to go with it. And I want to look at sketching one period of the function y equals 0.5 tangent pi over 2 of x. Okay, and so I'm going to be keeping some of this in mind. I'm going to kind of move up here so I can see a little bit of it. So the first thing I want to do is kind of identify my A and B of this problem. And you can see based on what we already wrote here, that here is my A and here is my B. And so I'm going to use those two factors there of A and B to kind of move some things around and identify them. So we can first see, kind of looking at the period of this function, our period is equal to pi over the absolute value of B. So if I think of pi over the absolute value of B, pi over 2, well, the absolute value is not going to change it up for me, but we can see that this is going to be pi divided by pi over 2. Working with division of your fractions, I'm going to say keep it, change it, flip it. So this is going to give me a new period of 2. So if my new period is 2, and we have not talked about shifting this around any at all, then I can already start to see that the way that this is going to cycle through, it's going to have a period of 2. So if I cut that in half, that means I'm going to have asymptotes, because we saw in our original function that it went halfway over here and halfway over here. It went to pi over 2 and to negative pi over 2, but an entire period of pi. Same thing's going to happen here. I'm going to have asymptotes at x equals -1 and 1, because I'm taking that period and kind of cutting it in half. And again, this is because we haven't shifted any. And so if I come over here to my graph, I can put -1 and 1, and I know that I'm going to have asymptotes there. Okay, so I've got the period as 2. I've created the asymptotes in there. I know that this has not been shifted any, and we'll look at why and look at how we can find those here. So I know I'm going to be going through the origin. Then, if I want to kind of figure out what's happening halfway over here, kind of to figure out how this has been stretched or compressed any, let's kind of go halfway and see what's looking like at that point. And the original function we looked at going all the way over to pi over 2. So let's start here with pi over, and then we could see pi over 4 was at 1. Let's look at 0.5 and see what's happening at that point. So if I say, let's see, they're working with y. So let's see if I want y equal to 0.5 tangent of pi over 2, and let's pick our x to be 0.5. Just to kind of see what's happening halfway, and then we'll kind of know what's happening down here as well. So this gives me 0.5 of tangent of, let's see, that's pi over 2 times a half. Maybe a little bit better to see with my fractions. So it would be tangent of pi over 4. And we know tangent of pi over 4, we've actually already figured that out. Remember up here? Tangent of pi over 4 is 1. And so this would be equal to 0.5 times 1, so just 0.5. So I know that at 0.5, this value I plugged in, it's going to output 0.5. So I get this value. And then I can see that it's also going to be at negative here. So I'm going to get a graph something like this. Now, this is not the only way you're going to be seeing these tangents. We kind of just looked at the y equals a tangent of bx. And so what I want to do, let's go to part C. Let's look at one that has some shifts in it and kind of see how that one's going to look from there. So just kind of looking at graphing this general form, y equals a tangent of bx minus c plus d. And I want to kind of take it through some of the characteristics and then do an example and kind of look at it from there. So again, we can note some things. We see that the stretching factor is absolute value of a. Number 2, the period is equal to pi over the absolute value of b. The domain is anywhere that x does not equal c over b plus pi over 2 absolute value of b times k, where k is an odd integer. So a little bit of changes up there compared to what we did in part B. The range is from negative infinity to infinity. And then we're going to have vertical asymptotes at these values where our domain doesn't exist. There is no amplitude, if you'll notice. From sine and cosine, we got an amplitude. With tangent, we're not going to have that because we can see that kind of going up and down without stopping points because of our range. And this is going to still be an odd function. And so let's just kind of jump to number 5 and do an example with more of these, our kind of alphabet soup going on here. And so let's graph one period of the function y equal to -2 tangent of pi x plus pi minus 1. It's a little bit more difficulty going on with that equation. Okay, so it's definitely written in our form that we saw up here with our A, B, C's, and D's. And so let's kind of mark those here. I see that I'm going to have A, B, C, and D, and make sure you keep any kind of sign changes that's going on in that problem. And so first thing we can notice, just like we did in the other one, let's look at the period of it. Now we know that our period is going to be equal to that pi over the absolute value of B. So it's going to be pi over the absolute value of pi, which is equal to 1. So we know that we're going to have a period of 1. And so then that means it's going to be 1 total unit. You can see up here we had 2 total units. Now we need to take into effect that this is different than that previous example because it has some shifts that are involved there. So the period is 1, but since C is equal to -pi, you can see that here in our equation we have minus C. So right here you can see that this is going to be minus from the equation, -pi is your C value. You see that? So if C is -pi, then the phase shift is going to shift over. You can see that C over B is listed here. So what we're going to do to figure out kind of the phase shift and how they shifted that period off the origin is we're going to do C over B. So I'm going to take C of -pi over B, which is pi. And so it has a shift of -1. So when I'm looking at my asymptotes, we can see it's kind of where our period starts and where it ends. It's going to have a total period of 1, but it's been shifted by -1. Okay, so let's go back up to this one. So this is tangent x. Everything else is kind of based off of this. So first of all, we already know that our period is 1. So we're thinking it's going to be like a half. You know, we're thinking positive half and negative half. But if it gets shifted -1, it's going to take each of these and shift it over 1. And so our new asymptotes are going to be at, we're thinking 1 and -1, but if we shift everything over 1 unit negative, then they're going to be at x equals -3/2 and x equals -1/2. Let's just kind of add that on here and kind of see what we can get with it. And then kind of make my units a little larger here so you can kind of see them. So here's -1/2, -1, -3/2. Okay, so you can kind of see the asymptotes going from there. Again, when I started out here, my period already changed to 1. So I was initially thinking -1/2 to +1/2. But then I had a phase shift of -1, so I'm going to take my origin, I'm going to shift it to the left 1 unit, and so then that's how I got my asymptotes at -1/2 and -3/2 because of that shift. Other things that I can note, I know that, let me go ahead and write it here so I don't have to switch back and forth. I'm looking at y equals -2 tangent pi x plus pi minus 1. I see that that -1 is going to shift me some. Instead of being here at the origin, I'm going to be looking at being down here for kind of my central point. I also note that I have a negative in front of this. And as you remember with just basic transformations of function, that's going to cause me a reflection. And then if I were to plot 2 points halfway in between, I would be looking at -1/4 and -3/4. And those values come out to be, let's see, I get a point at +1. Trying to make it somewhat accurate here. And I get a point at -3. And so what this graph kind of looks like is something like this. I didn't really do my curve very good in here. So I want to look at the equation and see what's given. I want to figure out my asymptotes. I want to figure out how we went from my origin point, how it moved, and I'm going to do that by my shifts. And so I know that -1 is in the middle. That's the middle of the period. And then I know I had a vertical shift of -1, so that's how I found this point. Then I want to pick a point halfway in between from this point and my asymptote. So I'm going to pick about -3/4 and -1.25. I'm going to plug them into my equation and it output it. I can mark these points here. 1 and -3. And I'm sorry, I didn't curve these very good. Okay, so you can definitely see this one's a little bit different in the fact of how we did that first one. We first just dealt with kind of the period changing and it being stretched, but this one dealt with horizontal and vertical shifts as well. And so that's what we're going to do as we continue on with our other functions. I want to look at just manipulating the A and B, and then I'm going to add in looking at the C and D being there. Okay, let's see, where are we at in our outline? I got A, B, C. Okay, let's do part 2. And let's look at our secant graph. Okay, so let's first look at, I'm going to break it up into 2 here. I want to first look at y equals a secant of bx. And let's again look at some characteristics. So number 1, it has a stretching factor of a. Number 2, its period is at 2 pi over b. Number 3, the domain is equal to, well, we're going to see the domain is x does not equal pi over 2 absolute value of b times k, where k is an odd integer. Four, we're going to have some range issues. When you're looking at your range here, the range is going to be from -infinity to negative absolute value of a, unioned with the absolute value of a to positive infinity. You can see that I'm going to include a bracket on a because it does include this value. But I'm going to have a parentheses on my infinities because we'll never reach those values. Let's see, the vertical asymptotes going to happen at this value right here. Again, there is no amplitude, and this is an even function. Put this back up here. This is an even function, and that's because cosine is an even function. And remember the relationship between your secant and your cosine. If I were to say y is equal to secant of x, that is 1 over cosine of x. And so if you consider what you know about your cosine function, it had a domain of all real numbers. But when I go all real numbers into a reciprocal function of like this, 0 is going to cause me problems. So I'm going to have problems wherever cosine is 0. Then if you think about the range of your cosine, it had some restrictions on it, and so that's why your range is going to be restricted here. Okay, so it all kind of relates back to that reciprocal function of 1 over cosine. And so let's just kind of draw it out here. Now on this graph, I am going to draw my cosine function, and I want to show you how doing 1 over that is going to kind of help you along the way. Okay. Okay, so if I consider first my cosine function, so here's my cosine function, okay? What's going to happen is I am looking at secant being its reciprocal, and so I am going to be creating some asymptotes along the way. I'm trying to use a different color here. You can see where cosine is equal to 0. When that 0 becomes the denominator, it's going to have an asymptote. And so everywhere I cross my x-axis on my cosine function, I'm going to see an asymptote. And then I'm taking all the x values and doing 1 over that value. So you create graphs that look something like this. Now you can see here my x value being, well, excuse me, cosine of x. So I do cosine of 0, it outputs 1. So if I do 1 over 1, I do get 1. So they do have some touching intercepts along the way. But you end up with a graph that looks something like this. And so y is equal to secant of x. And so I wanted to draw the red graph with the cosine on there so you can see how the secant graph is created from that. Yes, it does share some points because these are at 1s. Yes, it does have asymptotes because, again, cosine is 0, and so it's going to create asymptotes there because I can't do 1 over 0 and get a value. It's undefined. And you can also see how the period is in relation to 2 pi because I can't just restrict it between the two asymptotes like I did with tangent. That would only give me this part of the graph. All right. And so I am at a good stopping point on that one. And so what I'll do is finish up the rest of this lecture into part 2. And then we can finish out the rest of the secant, do our cosecant, and then we will also pick up cotangent as well. And that will finish out all of our trig functions, how they can shift, what their graphs look like, how we can identify the period, and really kind of get the characteristics and ins and outs of the remaining of the trig functions. So I hope this first half of 8.2 went okay for you. We'll finish up the second half of 8.2 in the second video. And then if you have any questions along the way, please let me know. Hope you guys have a great day.